To lesson 3.3. Today we're going to talk about the mole. The mole is a counting unit established by chemists to look at the number of atoms in a sample. The number of atoms in a sample, according to Avogadro's number, or mole, is 6.022 times 10 to the 23rd. This particular number draws it out a little bit farther. Some textbooks will just say 6.02 times 10 to the 23rd. And so we're going to look at the mole concept, but first I want to show you a video, a TED Ed video, and so I'll let you go through this. Let me drag it over to the screen. All right.
Let's be honest, you operate in pretty rare air.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind. Avogadro was the first one to come up with this idea. Scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd. Not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
All right, I hope you enjoyed that video, and hopefully it enlightened you some. So let's continue with our discussion about the mole. This slide shows you several different samples of 1 mole samples of elements. And if we continue and look, so the 1 mole sample of aluminum contained this many atoms, but its mass was only about 27 grams. The 1 mole sample of mercury had this many atoms, and its mass was about 200. So if you go back and look at that, there's your 27 grams of aluminum, there's your 200 grams of mercury. So definitely have to put those on a balance in order to see the mass of those, because you can't tell the mass of those by looking. And that is another concept in itself called density. But anyway, I did actually kind of play with this critical thinking slide. Your hourly wage on this is very, very, very small. And so, you look at that. If you're offered $1 million to count from 1 to 6 times 10 to the 23rd at the rate of 1 number each second, then each second you would be paid 1.66 times 10 to the negative 18 dollars. And even if you take that number times 3,600, it moves the decimal over 3 places. So you're talking about some dollar amount times 10 to the negative 15. So your hourly wage would be very, very, very tiny. And so just don't jump on that $1 million. I also looked at, I kind of played with the numbers a little bit and calculated how long it would take you. If you said 1 number each second, it would take you 1.9 times 10 to the 16 years to count to a mole. So not an offer you should take up. When we use Avogadro's number in chemical calculations, we compare Avogadro's number to the periodic table. And so on the periodic table, we use the average atomic masses, or the atomic weight, and carbon is listed as 12.01. That means a 12.01 gram sample of carbon is 1 mole of carbon. And so we can convert those things because with unit factors. To be honest, we don't use Avogadro's number a lot, and unless you see a problem that asks for or gives information in atoms or particles or even ions, you're probably not going to use Avogadro's number. So we'll use it in this lesson, and we'll use it occasionally after that, but don't just jump to 6.022 times 10 to the 23rd every time you see the word moles. That's the derivation of how they came up with the mole concept. What if you discovered Avogadro's number was not 6.02 times 10 to the 23rd, but 3.01 times 10 to the 23rd? And how would that affect the masses on the periodic table? So if Avogadro's number was 3.01 times 10 to the 23rd instead of 6.02 times 10 to the 23rd, that would be half as much. So you would have half as many particles. And so your relative masses on the periodic table, in order to have the same mass, would have to weigh twice as much. Just a math concept, but let's go ahead and move into some problems. Cobalt is a metal that's added to steel to improve its resistance to corrosion. Calculate both the number of moles in a sample of 5.00 times 10 to the 23rd atoms and the mass. So where are we going? We want to calculate the number of moles and the mass of cobalt. What do we know? We know how many atoms we have. So what are we going to use to get there? First, we're going to use Avogadro's number to get to moles, and then we'll use the molar mass to get to the number of grams. So here's the calculation. We start off with number of atoms. This was given in the problem. This is our conversion. We know that 1 mole is equal to 6.022 times 10 to the 23rd. We're going to add the proper units on here because we know we're dealing with atoms of cobalt, and we know that that many atoms of cobalt is 1 mole of cobalt. So if you do the calculations, you end up having 8.3 times 10 to the negative 4 moles of cobalt. if we look at the periodic table, we find out that the average atomic mass or the atomic weight of cobalt is 58.93 grams. So when we do that calculation, this is what the number we came up with for moles. And this is basically kind of a conversion because these two things are equal. 1 mole of cobalt has a mass of 58.93 grams. And when you're dealing with moles, you're going to see this a lot more than you're going to see 6.022 times 10 to the 23rd. But you go ahead and run that calculation, you end up with 4.89 times 10 to the negative 2 grams of cobalt. So a very, very small sample of cobalt for 5.00 times 10 to the 20th atoms. Another question here, what number of atoms of carbon are in a 1 carat diamond? So you know diamond is a form of carbon, and so a 1 carat diamond should be all carbon atoms. We're given that a carat weighs 0.200 grams. And so let's start out. Now notice it says number of atoms, and that means we're going to use Avogadro's number. But first, let's start off with what we're given in the problem, but 0.220 grams of carbon. Now we need to get in the common language of moles. And how do we go from grams to moles? We use the molar mass on the periodic table. And so we're going to go 12.01 grams of carbon in 1 mole of carbon. And then we know that 1 mole of carbon has 6.022 times, my writing is awful, times 10 to the 23rd atoms of carbon. And when you do that calculation out, you come up with 1 times 10 to the 22nd atoms of carbon in 1 carat. So a lot of atoms in 1 carat of carbon. Just a couple questions to end this PowerPoint. Which of the following was the most accurate description of a mole? So let's kind of talk through each of these multiple choice answers. The mass of carbon in a measured sample of carbon, does that define what a mole is? Well, it could if the measured sample was 12.01, but it doesn't say that it's 12.01. So we can't simply say that the mass of carbon in a measured sample of carbon is a mole. The number of atoms in any given mass of an element, same thing there. You know, we don't know the particular mass. And then on C, the number of sodium ions in 58.44 grams of sodium chloride. One of the things we haven't talked about yet is the molar mass of compounds, but if you calculate the molar mass of sodium chloride, you're going to find that it's 58.44. And each molecule, or sorry, each formula unit of sodium chloride is going to have 1 sodium ion. And so since this is a mole of sodium chloride, that's also going to be the correct answer. So your correct answer on this one's C. Again, they kind of jumped concepts on you in that particular question. This question, which of the following is closest to the average mass of 1 atom of copper? Notice it says 1 atom of copper. So none of these answer choices make sense because 1 atom is not going to be that massive. The only answer choice that even makes sense without calculating it is answer choice E, because 1 atom is going to have a very small mass. Now this question, you could do a lot of math with it, but all of the samples are 100 gram samples. And the one that's going to have the greatest number of atoms is the one that has the smallest molar mass, because if it has the smallest molar mass, a 100 gram sample has more moles. With more moles, you'll have more atoms. And so let's look at the periodic table. The molar mass of magnesium is 24.3. Zinc is 65.4. Silver is 107.8, and calcium is 40. So the smallest mass on that is magnesium. And so we have more moles of magnesium, therefore we have more atoms of magnesium. That completes lesson 3.3. The next time we're going to talk about molar mass.